Waves are our next topic in class, and a wave is a vibration or disturbance that transfers energy. A wave does not transfer material, but a wave can travel through material. And when it does, we call that material a medium. So a medium is the material that a wave will travel through. It will not carry that material with it when it travels. It will displace it temporarily, maybe move it up and down or move it back and forth, but it will not go with the wave. The formula for a wave is velocity equals frequency times lambda. This is a letter in the Greek alphabet, and we use it to represent wavelength. So wavelength times frequency equals speed or velocity, and that's how we'll calculate the velocity of a wave. Lambda will be measured in meters, that's the wavelength, and frequency is measured in hertz. Now a hertz is an inverse of a second, or we'll write it as Hz. Now what this frequency is telling us how many waves pass by a given point in 1 second. So frequency is a measure of how quickly the wavelengths pass by. So we measure that in hertz. Now a meters times a 1/2 is meters per second. Wave problems will be involving that formula that we just looked at. So here's an example. What is the speed of a wave with a wavelength of 0.14 meters and a frequency of 2450 hertz? Well, we identify our knowns. I have 2450 hertz and 0.14 meters. I'm going to label those. The hertz is frequency and the meters is wavelength. Check the units. If I had been given the wavelength as a centimeters, I would need to change it to meters before I put it into the equation. Now, substituting and solving, I have this equation, velocity equals frequency times wavelength. So the 2450 times the 0.14 gives me 343. But 343 what? Well, a hertz is 1/seconds times a meter. So a meter over seconds is velocity. Again, always putting in my units will help me make sure that I've done my equation correctly. Velocity should be measured in meters per second. Now I have this triangle that we can still use here, frequency times wavelength on the bottom with velocity at the top. So for those of you that need the mathematical triangle, you have one that you can use for these problems. I want to talk to you about the types of waves. Our first type here is the transverse or electromagnetic wave. An example of that is the light wave that you're very familiar with, I'm sure. We have the definition for a transverse wave is that it travels at right angles to the medium. Now, the medium, remember, is the material that the wave travels through. And if the energy is traveling at right angles, then we could say that it's traveling in a perpendicular direction to the material. Now, transverse waves do not have to travel through a medium, so they are able to go through a vacuum. I'm not talking about the ones that clean your carpet here. We're talking about the ones without air or material in them. A vacuum is empty, like space. Okay? Now, here's a diagram of a transverse wave, and if you notice, we have this up and down motion that we refer to here. The energy, if you could imagine, is starting over here on this end of the board, traveling toward me, and as it travels, it displaces the material in an up and down fashion. So we have right angle motion. Now, this top point, the highest point, is called the crest, and the lowest point is called the trough. So I have two crests and two troughs in my pictures, and notice that each of them has been displaced from this normal line equally. So we have amplitude in both places, and we have wavelength from crest to crest and trough to trough. We also have wavelength from the beginning of the crest to the end of a trough, because by definition the wavelength is a complete crest and a complete trough. Now this reference line is where the material would be if the wave was not passing through. So it's the reference line or the normal line. The mechanical wave can also be called the longitudinal or compressional wave, and an example of it is the sound wave. Energy will travel in the same direction as the medium in a mechanical wave, and we say that this is parallel motion. It must have a medium to travel through, so this type of wave will not travel through a vacuum. Now, if you notice, this looks a little different from the other picture, because if we start over here on this end of the board, the energy is still coming towards us, but it's going to move the material in a back and forth motion. So sometimes the material will be pressed together. We call that a compression. Sometimes it will be separated and spread apart. We call that a rarefaction. Now, a compression and rarefaction together is called the wavelength of the sound wave. Now we still have amplitude here. The lines above are equally as high as the lines below are low. And we still have the normal line or the reference line. The things that are different here is we don't have a crest or a trough when we're talking about mechanical waves.